Welcome to this MIT A+B talk. My name is Raphael Wu and I'm with the Reliability and Risk Engineering Lab at ETH Zürich. Today I would like to introduce our research on balancing costs, emissions and reliability in active distribution networks. The energy transition due to climate change is a many-faceted engineering and societal challenge involving many trade-offs. Today I would like to focus on three goals: the economy, continuity of supply, and sustainability of our energy systems. In most of the developed world, our energy systems are fairly cost-effective and reliable, but we need to drive towards sustainability. We investigate this trilemma of the energy transition in active distribution networks and microgrids. Active distribution networks are electricity distribution networks, including renewable generators such as PV panels, storage, or controllable distributed generators. A particular form of an active distribution network is a microgrid, which we define as an active distribution network which can operate in islanded mode by disconnecting at the point of common coupling. Our research question is: what are the cost, greenhouse gas emission, and reliability trade-offs in the transition from passive to active distribution networks? To answer this research question, we use a mathematical optimization model. For a given grid with characteristics such as the topology, line parameters, and electricity demands, for a set of candidate technologies with known greenhouse gas intensities and prices, we cast a multi-objective mixed integer linear program to optimize the installed capacities, technology dispatch, grid imports and exports, and the binary variable for a transition from an active distribution network to a microgrid. More on that later. We try to minimize three objectives: first, the cost; second, the greenhouse gas emissions; and third, the SAIDI, which is the system average interruption duration index and quantifies the expected duration of grid outages for each customer. The constraints are mainly energy balances, a power flow model, modeling of the technology behavior, and reliability. The resulting multi-objective mixed integer linear program is solved with an epsilon constraint, column and constraint generation solution. More on that later as well. Now I would like to focus on the reliability model, as this is the most innovative part of our research. In terms of reliability, we model two kinds of outages. The first kind is internal, so line and bus failures, where our lines and buses are characterized by a failure rate lambda and by a repair time tau. For a particular node, for instance, the one at the bottom right, we need to model the path between the node and the point of common coupling to find the buses and lines which contribute towards the outage frequency and duration at this particular node. In addition, we consider self-supply. So we assume that if the local generation in one node exceeds the load, such as shown in the plot below with the green area where PV exceeds the load, the self-supply is possible. Thus, we reduce the resulting total outage frequency and duration by the fraction of time that the node can self-supply. The second kind of outage happens in the external grid. There we model different scenarios. So for each time step, there is the probability that an external outage happens, as indicated below. If we are in the active distribution network case, meaning that our binary variable indicating that we transition to microgrids is 0, then we have the same situation as above. It's still self-supply for buses with distributed energy resources. If the microgrid has been built, we allow islanded operation, which means that we can supply the local loads with local generation and storage, and the grid is energized. Still, some loads may be interrupted because we can prioritize high priority loads. For successful islanding, there are two conditions. The first and obvious one is that the microgrid is built. And the second one is that there is sufficient fast ramping power to avoid a blackout when we do the transition. The storage and other generators installed in the microgrid have to be able to pick up the power import at the time step before the islanding transition within times of an order of magnitude of 1 second. With the reliability and overall optimization model set up, we need to define a solution method, because mathematical programming is inherently single objective, but we want to minimize cost, greenhouse gas emissions, and SAIDI. To do so, we first optimize each objective independently. As shown on this sketch of greenhouse gas emissions versus SAIDI, we get 3 points. A is the cost optimal solution, B is the greenhouse gas emission optimal solution, and solution C minimizes the unreliability. As a second step, we discretize the solution space into N1 SAIDI levels, and for each level, we run again a cost and greenhouse gas minimization, which results in the points D and E respectively, while we constrain the SAIDI to be below this level. As a next step, we discretize the space in terms of greenhouse gas emissions, and finally run optimizations constraining both SAIDI and greenhouse gas emissions, which typically yields a point in this corner, as this is the minimum cost solution for a given SAIDI and greenhouse gas emission constraint. And this way, we explore the entire solution space of 3 objectives. The developed model and of the solution method is applied to a distribution network in California. As we don't have the topology of a real grid, we take the benchmark topology of the IEEE 123 bus system, but the reliability values and other values are specific to California. Particularly, the failure rates and expected durations of external grid outages, line and bus failures are tuned to published data from the California Public Utilities Commission. In terms of candidate technology, there are 3 options. First, a lithium-ion battery. Second, a microturbine fueled by gas. And third, photovoltaic panels as a renewable generator. They are modeled here with affine cost functions, meaning that there's a constant, a fixed cost, and a capacity-dependent linear cost. For the point of common coupling, there is also a cost for the peak capacity that we consume, which is intended to incentivize peak shaving. There are 2 kinds of operation costs, first from the microturbine, and second for grid electricity imported at the point of common coupling. As we use a real-time price profile from the California Independent System Operator, there is a distribution of prices for electricity import, which is shown in this violin plot. In terms of greenhouse gas emissions, we consider both embodied emissions and energy-related ones. On the left, you can see the embodied emissions for the lithium-ion battery per kilowatt hour of capacity, whereas on the right, for the microturbine, grid electricity, and PV, we consider energy-related greenhouse gas emissions. In California, the grid mix is relatively clean, thus the emissions are lower than compared to the natural gas-based microturbine. Applying the optimization model to our case study yields the following trade-offs in terms of the greenhouse gas emission, SAIDI, and costs space. The reference system, meaning a passive grid, is here on the bottom, so with a greenhouse gas emission coefficient corresponding to the grid emissions and no distributed energy resources installed. The ideal, the utopia point, would be in the origin, because we want to minimize both the equivalent annual cost, EAC, greenhouse gas emission, and third, the SAIDI as well. To show more quantitative data, I'm going to switch to a projection onto the greenhouse gas emission and SAIDI space, while the equivalent annual costs are color-coded. Additionally, there are lines of ISO cost curves, but they're just interpolated. The real solutions are indicated as dots on this scatter plot. Starting from the reference solution, we can see that there are a variety of paths to reliable grids. One can go with a rather low cost and high emission path, or when one wants to reduce the greenhouse gas emissions significantly and improve reliability, costs increase. By the almost vertical ISO cost curves, one can see that greenhouse gas targets drive costs more than reliability when going significantly below the current reference level. In terms of SAIDI solutions, when reducing the SAIDI, the solutions are rather stratified, meaning that the cost-optimal solutions are always at the SAIDI limit. Whereas for greenhouse gas emissions, we have significant gaps in the solution, which highlights the importance of exploring the search space, because even though we constrain the greenhouse gas limit to be within this red circle, the next cost-optimal solution actually has much lower greenhouse gas emissions. In terms of the optimum design, the obvious way to reduce greenhouse gas emissions is to install more PV, as we can see on this plot of the installed PV capacity. In terms of reliability improvement, the higher emission solutions employ a microturbine, which is then replaced by a combination of PV and storage to provide backup when the sun does not shine. The point of common coupling is slightly undersized, meaning that the capacity is below 1 kilowatt per kilowatt peak of load when we have a microturbine, which can also help with peak shaving. But when we move towards lower greenhouse gas emission and higher SAIDI solution, where we only have PV, which is exported in times of PV excess, the point of common coupling connection is slightly oversized compared to the load. In terms of energy supply, I'm going to show them on this plot with the red guidelines to show how to interpret it. For this particular solution, there is no energy supplied from PV on the right axis. About 25–28% comes from the grid, whereas the remainder, 70% comes from the microturbine. When we reduce the greenhouse gas emissions from blue to white, the solution moves from a microturbine and grid-based solution to a grid and PV-based energy supply. On this axis, we also see an increase in energy self-sufficiency because both microturbine and grid electricity are imported, while the PV energy is locally produced. Finally, the reliability is independent of the energy self-sufficiency, as we can see that with the SAIDI on the color code, we see all colors on this line, which is mainly due to storage, as one can install storage to improve the reliability. In terms of reliability, we can see on this plot the bus self-supply in terms of the percentage of customers' hours where nodes can supply themselves. With decreasing SAIDI, the ability to self-supply increases, but there is also this pocket of high self-supply at about 3 hours per customer per year. This is due to, this can be explained due to the transition to microgrids. For higher SAIDI values, it's sufficient to install a few distributed energy resources for nodal self-supply in key nodes, but as we move below 3 hours per year, a microgrid is built. This is because 66% of the outages happen outside the active distribution network, thus a microgrid transition makes sense to reduce SAIDI. Building the microgrid allows for SAIDI reduction by supplying important nodes, as shown on the right here, where we go from 100% interrupted before the microgrid is built, all the way down to 0% interrupted when all loads are supplied. Finally, I would like to conclude with the main trade-offs that we found in the energy transition trilemma for active distribution networks. First, a significant reduction in greenhouse gas emissions increases costs, but also energy self-sufficiency. For most of the greenhouse gas emission levels, the reliability can be improved at similar costs. And finally, within the trilemma, there are clear trends in the optimal technology mix and in the decision to go from an active distribution network to an islanding microgrid. Thank you.